The explosive growth in mobile devices and applications poses significant challenges to the forthcoming sixth-generation networks to handle user demands in a wide range of fields, such as high-speed data services, high-reliability transmission, and high-precision sensing. Evolved from massive MIMO, ultramassive MIMO is expected to be one of the most powerful technologies to satisfy such stringent requirements in 6G networks due to its capability of highly directional beamforming. However, inherent defects of standard massive MIMO enabled by phased arrays limit the future development of ultramassive MIMO systems. Specifically, the half-wavelength element spacing of the phased array restricts its directive gain for a given physical dimension. In addition, as the physical dimensions of phased arrays relying on costly components such as phase shifters scale up, the implementation of ultramassive MIMO with phased arrays in practical system becomes prohibitive from both cost and power consumption perspectives. Against this background, a new paradigm termed holographic radio for ultramassive MIMO has been developed. Specifically, in the vision of holographic radio, numerous tiny and inexpensive antenna elements are integrated into a compact space to achieve high beam pattern gain with low hardware cost. We propose a practical path to implement holographic radio by a novel metasurface-based antenna called Reconfigurable Holographic Surface. Specifically, the RHS incorporates feeds and densely packed sub-wavelength metamaterial radiation elements. As a kind of leaky wave antenna, the RHS uses series feeding where the reference wave generated by the feeds propagates along the RHS elements and excites the RHS elements one by one. The series feeding adopted by the RHS leads to a much simpler wiring layout compared with parallel feeding adopted by phased arrays where a feeding line is required for each antenna element. Based on the holographic interference principle, each RHS element controls the radiation amplitude of the reference waves electrically to generate desired directional object beams. Such a beamforming technology is also known as holographic beamforming. Different from another type of metamaterial-based antenna called reconfigurable intelligent surface whose feed is set outside the metasurface due to its reflection characteristic, the highly integrated feed structure enables RHS to serve as an antenna array deployed at the transceiver directly, and thus provides a practical path toward the implementation of holographic radio. To fully exploiting the potential of amplitude-controlled holographic beamforming, we aim to develop a general holographic beamforming optimization algorithm for beam pattern gain maximization. The beam pattern gain is an important metric to indicate the directivity of generating beams, where a higher beam pattern gain can enhance the data rate of communications and the spatial resolution of sensing. Hence, the developed algorithm is applicable to various scenarios. However, the RHS also presents the following three challenges. First, designing an RHS is challenging since the RHS elements are coupled with each other due to the serial feeding structure. As a result, it is necessary to perform overall optimization design of the RHS using parameters obtained from effective medium theory and conducting full-wave simulation analysis. Second, the practical radiation characteristics of RHS elements differ from the ideal model due to the influence of RHS hardware design. Therefore, full-wave analyses are conducted to analyze the radiation characteristics of the RHS elements, based on which a holographic beamforming optimization algorithm considering practical radiation characteristics of the RHS elements is developed. Third, the development of a novel amplitude-controlled holographic beamforming optimization algorithm is required since traditional phase-controlled analog beamforming schemes cannot handle the real-domain amplitude constraints. To tackle this challenge, we decouple the radiation amplitude of each RHS element from the holographic beamforming matrix to reformulate the beam pattern gain maximization problem as a quadratic optimization problem, such that the properties of the optimal solution can be revealed. From the optimal solution, we find that an RHS loaded with PIN diodes capable of binary discrete amplitude control is enough for beam pattern gain maximization. To verify the feasibility of RHS-enabled holographic radio, we implement a prototype of RHS operating at 12 GHz. First, we design the hardware of an RHS element. An RHS element capable of controlling the radiation amplitude of the reference wave generated by the feed relies on a complementary CELC resonator loaded with PIN diodes. The whole structure of the RHS element consists of the following 5 layers. The top layer is the microstrip line etched with the CELC resonator. The second layer is the radio frequency substrate to guide the propagation of the reference wave. The third layer is the ground plane made of copper. The fourth layer is the spacer dielectric layer to separate the ground plane and the direct current bias feed line. The bottom layer is the direct current bias feed line to apply biased voltage to the PIN diodes through a via extending through middle 3 layers and the CELC resonator. For symmetry, 2 PIN diodes are connected across the gaps separating the microstrip line from the central metal patch. The on and off states of the PIN diodes are controlled by applying different biased voltages. The radiation power of the reference wave is determined by the states of the PIN diodes. Specifically, when the 2 PIN diodes are in off states, the radiated power will be large. In contrast, when the PIN diodes are in on states, the radiated power will be small. Based on the RHS element design, we implement an RHS consisting of a 2-dimensional array of controllable RHS elements. The RHS is placed on an antenna rotating platform for beam pattern measurement. In addition, there are 4 feeds attached to the left end of each row. The reference wave generated from each feed propagates to each RHS element and radiates energy to free space. The residual energy of the electromagnetic waves will be absorbed by the matched impedance attached to the right end of each row. The radiation amplitude of each RHS element can be controlled based on a FPGA. Specifically, a software program is preloaded in the FPGA. The bias voltage applied to each PIN diode can be changed by controlling the FPGA, such that the on-off state of the PIN diode together with the radiation amplitude of each RHS element can be controlled. To verify the effectiveness of the proposed holographic beamforming scheme with practical model, we evaluate the beam pattern of the implemented RHS by comparing it with the proposed algorithm with ideal model and the uniform superposition scheme. We observe that the beam pattern gain obtained by the proposed algorithm is larger than that obtained by the uniform superposition scheme, validating the effectiveness of the proposed algorithm. Moreover, when the amplitude of an RHS element is set according to the practical model rather than ideal model, the beam pattern gain of the RHS can be further enhanced. We also compare the proposed holographic beamforming scheme with conventional phased array 1. The power consumption of one on-state PIN diode in RHS is 0.01 watt. And that of one phase shifter in phased array is 1 watt. With the same power consumption, the RHS outperforms the phased array in terms of the beam pattern gain, implying that the RHS provides a powerful solution to reduce power consumption while guaranteeing high beam pattern gain in practice. Based on the prototype of the RHS, we develop an RHS-aided communication platform, which are composed of the transmitter, TX, side and the receiver, RX, side. The TX side includes the TX host computer, the TX USRP and the implemented RHS. The TX is implemented by utilizing a Universal Software Radio Peripheral, USRP, which generates transmit signals and sends the signals to the RHS. The TX host computer can control the parameters at the TX, such as the carrier frequency and modulation mode. For the RX side, 2 RXS are implemented. The RX side includes the RX antennas, the RX USRP, and the RX host computers. Each RX is composed of 1 USRP and 1 standard horn antenna. Specifically, the RX USRP is used to process the signals received from the standard horn antenna. The RX host computers can display the recovered signals and the corresponding parameters, such as the spectrum and constellation. The RHS-aided communication platform is deployed in an open space to evaluate the data transmission performance in a general scenario. The RX1 and RX2 are deployed at the orientation of the RHS at angles of 0 and 60, respectively. The distance between the RHS and each horn antenna is set as 2 m. The transmit power of the TX USRP is 10 dBm. In the deployed RHS-aided communication platform, we transmit a real-time 1080p video using the 16QAM modulator. The frame rate is 30 frames per second. Each RX achieves a signal-to-noise ratio of about 26 dB in the experimental environment. As shown in the constellation diagram, the 16 points are equispaced around a circle, implying that the received signal is demodulated successfully. Besides, the received videos from both RXS match the transmitted one. This validates that our RHS-aided communication platform supports real-time transmission of high-definition video. Moreover, the power consumption of the RHS-aided communication platform mainly comes from low-power hardware, including PIN diodes, control circuit, and FPGA. The total power consumption of the platform is only 0.686 watt. In conclusion, the RHS demonstrates promising potential in achieving high beam pattern gain with low power consumption and low hardware cost, thereby providing a practical path towards ultramassive MIMO.